Hello, my name is Colton Cavilla and I'm doing a presentation today on ballistic simulation. The presentation will be on simulating a micrometeoroid impact on the ISS Cupola window. So an overview, I'm going to go through the motivation, the background, objectives, geometry, the boundary conditions, mesh optimizations, simulations, discussion, and finally conclusions. So the motivation for this project is that um, I will be working for NASA once I graduate this spring, starting in less than a month actually, and I'm going to be working in a branch that does hardware for the ISS, mostly life support systems. But I figured this project would be interesting given the context of this class and the work that I will be doing in the future. So micrometeoroids present a constant threat to vehicles in low Earth orbit, and so vehicles up there must be designed to withstand these impacts. Another motivation, I haven't had much experience with these types of simulations, explicit dynamics, so I wanted to learn and experiment with it and just try to get a better understanding of how it worked. So a little background on the project. So the cupola window on the ISS was installed, I believe, in 2010. It is an 80, the top window, the one that I'm focusing on, the big round window on the top is 80 centimeters in diameter. The purpose of the cupola and the reason why they wanted to make these large windows was to provide an observation area for the ISS crew. It's mostly looking at the Earth, so it gives visibility to the Earth, so they can take pictures and do different experiments through these windows, and also they can look at celestial objects as well. So it has 6 windows around it. It's a hexagonal shape, and the top window, the one that I'm focusing on, again, is 80 millimeters in diameter, and it's comprised of 4 different panes of glass. The one facing the outside is called the debris plane. It's about, as you can see right here, 94 centimeters thick. Then there's a vacuum gap in there. And then there are 2 pressure panes, and so each of those is 3.68 centimeters, and then there's a scratch pane on the inside that I guess is probably easily interchangeable if they need to change that out. And here's just a schematic of a cut view of how it's assembled. You can see there it's kind of bolted with different flanges here to keep the windows in place. What I ended up doing was a very simplified version of this for my analysis purposes. So the goal of this project is to determine whether changing the shape of the flat circular glass on top of the cupola to a dome shape would dissipate the energy of a micrometeoroid better, and thereby protecting the inner panes and ultimately keeping the astronauts safer from micrometeoroids. The objectives to do that would be to make a simplified 2D axisymmetric CAD of the cupola window, which includes all 4 panes, run a 2D simulation of a 2 millimeter diameter spherical micrometeoroid hitting the simplified window at 10 kilometers a second. So 2 diameter was kind of the biggest average size debris on the larger end of the average size debris that they run into hitting the ISS. So I wanted to kind of make it a worst case. And 10 kilometers a second is also kind of a worst case speed. So I wanted to design for the worst case. So to do that, I ran a mesh study and I analyzed the results after running the simulation. So after I did that, I repeated the simulation with a dome-shaped window to compare the results, and finally I determined with those results which window shape is better at dissipating impacts of micrometeoroids. So the geometry, here's the schematic of a 3D schematic of the cupola window that I made. You can see all of the panes in here, the outer pane, the two pressure panes, and the inner scratch pane. And with all the same dimensions that I just mentioned. And then you can barely see a micrometeoroid that I made in the form of just a sphere that's 2 millimeters in diameter. You can make it out right there, and I put it at 1/10 of a centimeter away from the edge of the glass, the top edge of the glass there. So that's the 3D geometry. Of course, I simplified it to a 2D axisymmetric geometry. So here is the complete 2D axisymmetric geometry. You can see here all the same dimensions. This is only half of the window right here. It's 40 centimeters, and then here's a detailed view of the half of the meteoroid, the little gap, the 1/10 of a millimeter gap right there, and then the edge of the top pane. And so this will all be axisymmetric about the y-axis right here. So here are the values, and on to the next. So boundary conditions. Had a couple boundary conditions. I fixed the windows at the right side of each of them. And the reason I didn't want to mess with actually putting the plates in there and doing some other kind of support was because this micrometeoroid is going so fast and it's so small that really these won't see that much load. The glass shattering will take the most of the load. That dissipation energy will take most of the load, so it's really not that important to make these realistic to what you see on the actual cupola window. The other boundary condition was the velocity of the micrometeoroid, and here you can see it's the equivalent of 10 kilometers a second. So mesh optimization. I used edge sizing to refine mesh areas of interest. I used all triangles on the micrometeoroid to get a little better mesh out of that, and I adjusted the element sizes to meet the limitations of my academic license, was 32,000 nodes. Here you can see the automatic generated mesh. This was just the edge of the windows, and you can see the little meteoroid up there, and here's a zoomed in view of just the meteoroid in this top box, and you can see the mesh is much too coarse for me to get any of the results that I need, and it would be a terrible simulation. So I did some edge sizing, and you can see we have a lot better mesh along the edge, which should give us much better results. For mesh optimization, I did a study, and I did a study of starting with 4 millimeters as a mesh size. I went down to 2 millimeters, 1 millimeter, half a millimeter, quarter of a millimeter, and then 1/10 of a millimeter. And you can see here the value of the stress, von Mises stress value as that gets refined. And as you can see in the graphs here, starts off very low. As the element size is bigger, the stress is very low. And here you can see a drastic increase from, it looks like the 2 millimeter element size to the 1, and then it continues to increase, and then it kind of looks like it tapers off here and kind of gets almost a linear pattern going here, but it also looks like it's tapering off. So I decided at 1/10 of a millimeter that would be sufficient for my purposes. So here's more detail about mesh optimization. I used an element size of 2.5 millimeters. This gave me an edge sizing of 0.1 millimeters, which gave me this finer mesh at the edges and a growth rate of 1.05. This gave me 28,692 nodes and 27,634 elements. And here is the mesh optimization for the dome hemispherical shaped window. I used the same parameters, which gave me 30,907 nodes and 29,664 nodes. And here at the bottom are my mesh metrics, which are skewness, or aspect ratio rather. So you can see we have a pretty good mesh going here. So for the results of the simulation, I looked at max equivalent von Mises stress to see what kind of forces the glass panes were absorbing. The flat window results gave me a maximum equivalent stress of 81,000 megapascals, and the hemispherical window gave me a max equivalent stress of 72,000 megapascals. So we can see here kind of a time lapse of the simulation on the flat window. I have a video on the next slide. Here is a time lapse of the curved, the hemispherical window. So you can see here they're kind of similar. So here's a simulation of the flat glass. You can see it's kind of interesting. It looks like a chunk of glass is flying up there. And on the next slide, we have the hemispherical window, and you can see it's a little different. There's no chunk flying up there, so it's kind of interesting to see the difference there. Okay, so the outcomes, the hemispherical window saw less stress than the flat glass, so it might be able to withstand a little bit more force, though the hemispherical window is obviously more heavy and likely costs quite a bit more to make. So the trade-off for replacing the current setup and design on the ISS for this hemispherical window actually is probably not realistic. So some other thoughts, explicit dynamics simulations are computationally expensive, extremely sensitive to input parameters, and they take a lot of time. This was a very simple simulation, and it still took a lot of time, and I had a lot of trouble fiddling with different settings to try to get it to work. So another thing, I had trouble getting the 3D simulation to work. I wanted to run a 3D simulation to verify my 2D results. I wasn't sure, but was thinking it was possibly because of the academic license issue. Quality of mesh is very important to getting an acceptable and realistic results. And lastly, there were elements of the micrometeoroid you could see in those previous videos of the simulation that went down along the y-axis of the axisymmetric simulation. And I'm not sure how accurate those were. Some of those elements kept going to the next pane, but it kind of turned into a line, a flat line of red elements going down, and that seemed a little questionable to me as to how accurate those were and how far they'd actually keep going down. So in conclusion, the goal again of my project was to determine whether changing the shape of the circular glass on top of the cupola dome to a dome shape would dissipate the energy of micrometeoroid better and protect astronauts also a little better. The goal was achieved, though clearly more research should be conducted were this to actually be considered as a serious option for the ISS. This was a great project to help me better understand what engineers have to design for with low Earth orbit vehicles and satellites, and how they ultimately analyze their designs to make sure they're acceptable. As for future work, running 3D simulations to verify the 2D results would be, I think, the first step. And lastly, here I am. Again, my name's Colton Cavilla, and that's my email and my phone number. Thank you.